Okay, we're back again. We'll cover another section here, and I'll probably do that for the next couple ones, just cover section by section and post those. And I'll be looking to get some office hours on Zoom. So like always, just pay attention to Canvas and look in the announcements for any changes. So in the last section, we talked about what were known as the aldol reactions, where we took aldehydes or ketones, deprotonated, generated an enolate, and attacked another carbonyl. Well, we do have another set of carbonyls that we can consider as electrophiles, and those are esters. So these were discovered by Claisen and are known as the Claisen condensation reactions. You notice they're a little bit different than the aldol reactions. In this case, what we get out of a Claisen reaction is always a beta keto ester. And so where does that name come from? So again, we have the alpha position, we have the beta position. And so if you notice at the beta position, there is an ester, and we also have a ketone. So we generate a beta keto ester from the Claisen condensation. And so what we do is we take two esters and we mix them with a base. And notice the base that we're using. In this case, it is sodium ethoxide. And there's a reason that we choose that base, and we'll talk more about this later. But this base can actually attack, kick up, down, and kick out the leaving group. So what you'll notice is the base that we use in the Claisen condensation always matches the type of ester that we have. So if we have an ethyl ester, we're going to use an ethoxide as the base. And that prevents unwanted side reactions. So let's look a little bit closer at the Claisen condensation and see what is happening. Nothing new in the first step. We pull off an alpha proton and park those electrons at the alpha position. And then as we move across, we have this enolate that is looking for an electrophile. And in this case, it is going to be the carbonyl of an ester. So we kick those electrons up onto the oxygen. And in the aldol reaction, we stopped here. But the reason that we stopped there is because we didn't have a leaving group. The key for the Claisen reaction is we actually now have a leaving group on there. So just like we saw in the aldehyde and ketone chapters where we did addition reactions, in the carboxylic acid derivative chapters where we did substitution reactions, since we were doing a substitution reaction, we have a leaving group. And since we have a leaving group, this negative doesn't stay on the oxygen, but collapses down and kicks off that leaving group. And then we get this carbonyl here. Now, if you notice, the product that we actually make is a dicarbonyl. And so this H right here is now much more acidic. This over here has a pKa around 23, if I remember right. And this here has a pKa around 12-ish. So we actually make a much, much more acidic alpha proton once we make these products. And so what happens is the base that we use immediately deprotonates, and we actually end up with this until we work up the product. In the aldol reaction, it's actually base catalyzed. We actually generated an OH minus in the condensation reaction. Here, we actually have to add a stoichiometric amount of base. We have to add 1 mole of this for every 1 mole of this. And the reason for that is because we generate an acidic proton. And so we deprotonate that, we generate the alcohol, and we end up with this resonance stabilized enolate. So the Claisen condensation reactions are reversible. So What we want to do is understand how we can obtain a good yield of the products. And the alkoxide's not a weak base and may reverse the reaction by serving as a nucleophile. And so if this, and as I just mentioned, if we have this base here, it can come and deprotonate this dicarbonyl compound. So it requires a full equivalent of the base rather than a catalytic amount. So let's look at this a little bit more in depth of why we want to use the alkoxide and why we just don't use sodium hydroxide, and look at the limitations to the Claisen condensation. So it's required that the starting ester has 2 alpha protons. So here we would actually need 2 alpha protons to help drive this equilibrium forward. And the other limitations is we can't use sodium hydroxide. And this goes back to our carboxylic acid chapter. If we take an ester with sodium hydroxide, it can attack that carbonyl. We actually kick off the alkoxide here, generating a carboxylic acid that is then deprotonated. I'll give you 2 bonus points if you can remember the name of this reaction. And if you said saponification, you just got yourself 2 bonus points. Write those on a piece of paper and store them somewhere for your mom to give you a gold star. So this O- can deprotonate the carboxylic acid and we generate a carboxylate. So we don't want to use sodium hydroxide as a base in the Claisen reactions. As mentioned earlier, we also tend to use the base that matches the ester. So in this bottom example here, we have a ethyl ester, and so it would be much better to use a ethoxide than a methoxide. And the reason for that is if we used a methoxide, we could actually attack the carbonyl, kick the electrons up onto the oxygen, those would collapse down and would kick off the OET. We may kick off the OMEA as well, but at some point we would kick off the OET and we would now end up with a methyl ester. And so in solution, we would have a mix of methyl esters and ethyl esters in there. So just to avoid this reaction, again, 2 bonus points if you can remember the name of this reaction. So to avoid this, we use the base that corresponds to the ester there. So this will still attack. I'll show that in blue arrows. So this can still attack up, down, and it would kick out the OET. But when we did that reaction, you wouldn't notice a change because the transesterification, that's the name of the reaction. So again, 2 bonus points. Make sure your mom gives you a golden star for that. The transesterification reaction gives you the same product back. So watch for that. You'll always use the base that corresponds to the ester, and we won't use the sodium hydroxide to generate the enolate in this case. So just as we did in the aldol reactions, we can mix it up and we can do what's referred to as a crossed or mixed Claisen condensation. And we have the same issues that we would have in the aldol reaction. That is, if we don't practice control, then we can actually get a bunch of mixed products. So we play the same tricks, and those tricks are we choose a molecule, or we choose a reaction that only has 1 set of alpha protons. So you can see in this case here, we have the ethyl acetate, which we list as the donor. It's the only one with alpha protons there. We choose the acceptor, or the one that's going to be the electrophile. It has no alpha protons. And we can also play a trick of picking a strong base. So you could either use sodium ethoxide here, or you could use a strong base. And so what would happen is a strong base can deprotonate the alpha protons, only those that are available on this molecule. And then you'd have this sitting in solution, and you'd add the ethyl benzoate, and you could get your beta keto. So the keto is beta to the ester there. So notice we got 2 carbonyls and an ester right here. And this is a mixed one. So we've actually combined 2 different esters to make a new product. So experimental notes, notice a base typically employed as a poor nucleophile or the same as the leaving group of the ester. And when we say poor nucleophile, something like NaH, so it doesn't hydrolyze or react, substitute that ester. And again, what we can do is we can add just one compound that has alpha protons, and our other one lacks alpha protons. And so what we do is we have the one listed in excess sitting in solution. We add the ethoxide, and those two, nothing happens. Then what we do is we add the compound with alpha protons slowly. And so the key is, as we add this slowly, it gets deprotonated, forming the enolate. And since it's in low concentration, it's much more likely to find the species that's in high concentration and react. And then we get the product. Notice in this case, they're working it up with a little bit of HCl. It'd probably be better just to say some H+, maybe not HCl. And the reason for that is, if we crossed out that step 2, the product that we would actually isolate is the negative here. Remember, when we generate this beta keto ester, we make a molecule with a much more acidic alpha proton. And so the base that we use will actually come and deprotonate that. So if we look at this top example here, notice these H's, they're very acidic. And notice in the workup, we always add a little bit of acid, because if we didn't, we would end up with the deprotonated species, like shown down here at the bottom. But once we add a little bit of acid in the workup, we protonate that to get a neutral species. So not only can we do self-Claisen condensation reactions, we can do mixed using the same logic that we did in the aldol condensations. We just have to control those reactions. So here's kind of a summary of that. So one ester has no alpha protons. We can do a reaction. In this case here, we would pull off the protons at the alpha position of the species that contains the alpha protons. The red species doesn't, so therefore there's going to be no reaction between the base and the species with no alpha protons. The species that we did deprotonate then acts as the nucleophile and can attack, kick off the leaving group. And again, notice in this case here, we're lacking the acid workup, and so the product is actually negative. So what you'd need is a step 2 with a little bit of acid. That would protonate at that spot, and you would end up with your neutral product. So just remember, in the Claisen reaction, you're going to need to work it up with a little bit of acid, not too strong, but a little bit of acid to actually get the neutral product. Just like we saw in the aldol reaction, you can use LDA. Again, notice that this is an irreversible arrow in this bottom example here. We get 100% enolate, and it just sits around in the reaction waiting for an electrophile. So you first add the LDA, wait for the reaction to complete the deprotonation, Once that occurs, you add in your acceptor or the electrophile. It will attack up, down, you kick off the leaving group, and you end up with your product. Again, the first product that you would end with, or that you'd get right after the substitution, is the condensation. But remember, we just generated a compound that has much more acidic protons. And so a base will come and deprotonate those. And so again, you need the workup to get to your neutral species. Let's try that again. And then you have your neutral species that you can use for whatever purpose you want. Okay, so we can do this reaction and make very interesting molecules. In fact, we'll see these beta keto esters later on. They're actually very useful molecules. And so again, in this case, we just need to be careful of the base that we use. But notice here, we're not actually reacting between two esters. So in this case, we're actually using a ketone and we're reacting with an ester. So this is kind of a mixed aldol Claisen. I believe it's called a Claisen-Schmidt, but don't quote me on that. There's lots of variations on this reaction and lots of people threw their names on these reactions. So notice in this top example here that we're actually using a ketone. We've got some alpha protons here. Our acceptor doesn't have any alpha protons there. And so what we're going to do is take advantage of these alpha protons, even though it's not a ester. So this is more like an aldol type reaction, but we're going to deprotonate it and make an enolate. We're going to park a negative there. And those electrons would attack here, kick the electrons up, out, and kick off the OET. And so we end up, in this case, a beta keto aldehyde. So we don't have the ester because we didn't quite do a Claisen condensation, but notice we still do have this feature of two carbonyls that are 3 away. This is what you call a 1,3-dicarbonyl. That comes from a Claisen or this modified Claisen reaction. And down at the bottom, you can see another example. So we can actually combine kind of the aldol and the Claisen, but the mechanism here is the same in that we're attacking a ester, kicking the electrons up, down, and kick off a leaving group. And so we're going to end up with this 1,3-dicarbonyl here. And just like we did in the aldol reaction, to make it even more funner, we can actually do an intramolecular Claisen reaction. Now, this was discovered by Dykman, and as I just mentioned, there's a lot of variations on these reactions here. And so people threw their names on when they said, oh, look, Mr. Aldol discovered a reaction, and then they discovered that intramolecular aldol. And then Claisen came along and said, hey, I could do it with esters. And then Dykman came along and said, hey, well, I can do it with an intramolecular esters. And that is known as the Dykman cyclization. And so I'll stress again that you should know these reaction names on exams. Sometimes they just say, hey, draw an example of a Claisen or a Dykman or an intramolecular aldol or a aldol addition or an aldol condensation or an alpha halogenation. So far, those are the reactions that we've learned. Again, the alpha halogenation, the aldol addition, the aldol condensation, the intramolecular aldol. We just talked about the Claisen, and now we're going to talk about the Dykman reaction. So to do the Dykman, we need a single molecule that has 2 esters. Now this is a little bit easier to see than the intramolecular aldol because really all we have are two different types of, oh, sorry, I'm having technical difficulties. Just 1 second. Let's see if that fixed it. No. Okay, we're back. I think all these people online are causing some connectivity issues. So we're back to the intramolecular Claisen condensation known as the Deichmann. And as I was saying, this one's a little bit easier because we really only have two different alpha protons. And so we're going to do the same exercise that we did before. We're going to count from the alpha carbonyl, or the alpha carbon to the carbonyl. And so when we do this exercise here, we realize if I connected from this alpha carbon to that carbonyl, I would make a 5-membered ring. Same here, if I take this alpha carbon and count to the carbonyl, then it would make a 6-membered ring. So we're going to practice the exact same thing that we did before. We're going to count from one alpha carbon to the carbonyl and see how big the ring can be. And again, the rule of 5 or 6 will be key. We're going to want to form 5 or 6-membered rings. So I'll do abbreviated mechanism on this top example here. We would deprotonate that negative or deprotonate that alpha carbon, forming a carbanion. And then we attack that carbonyl intramolecularly, kicking off the leaving group, and we get a 5-membered ring. In this bottom example, same thing. We would form that enolate. Notice the base that we're using matches the ester. We're going to attack that carbonyl again and kick off the leaving group, and we get a 6-membered ring in this case. So just up here at the top is just to remind you that we want to use the ester, or the base that matches the ester. So this is just what happens. So this reaction is actually constantly ongoing in there. It doesn't produce a changed product. So it's what I refer to as a non-productive reaction, because the product you get is exactly the same as your starting material. So that is going on throughout this reaction. Even in these examples down here, that reaction is constantly going on. And that is why you choose the base that matches the ester. So we're going to ignore that because that's a non-productive reaction. And what we do is we identify our alpha protons and count 1, 2, 3, 4, 5 carbons away. And so I'm going to end up with a 5-carbon, or a 5-membered ring here. And again, it's going to end up a beta keto ester, just like a Claisen does. In this case here, we're going to count, there's our alpha carbon, we're going to count from it, 1, 2, 3, 4, 5, 6, and I end up with a 6-membered ring. So the mechanism for this is just as it is for the Claisen. We're going to deprotonate, park those electrons at that alpha position. You can see those parked there, and then we're going to attack the carbonyl, or the ester, within the molecule, kick the electrons up, get the tetrahedral intermediate that collapses down, and we kick off the leaving group. And again, we end up with a 5-membered ring. I always think it's good skill to be able to identify your alpha carbon. So there's your alpha carbon, and this is the bond that we made. So that is known as the Deichmann. We'll leave it there, and the next lecture will cover the alkylation of the alpha protons. keep studying, and don't forget to have fun.